Yeah, probably time to start. So it's my pleasure to introduce Professor Hone from University of Kent. He is going to start with, like as usual, like a short trailer, and then the talk is, the title is there, Heron triangles with two rational medians and discrete integrable systems.
Yeah, okay, thank you. It's very nice to be here, Lorenzo. Thanks for having me. It's great to be in Colorado. It's my first time in Colorado, and Anton here has been a wonderful host already, and I arrived at 2 p.m. on Monday, and so the jet lag is just wearing off. So yeah, I'll give you a short trailer, and in a way, this version of the talk on the slides was for in a conference. It was only like a 25-minute talk, so it's a small number of slides, and then I can explain more on the board if you're interested in more details. So what I'm talking about is, you could say, a problem in Diophantine geometry, which is looking for triangles with special properties. So to start off with, I'll tell you about Heron's formula. So this is a beautiful formula for the area of a triangle, which was found by Heron of Alexandria. I think that's sort of like 1st century AD or something. I don't remember. I should have looked up the history before giving the talk again, but I've forgotten exactly Heron states. So yes, it's in terms of this quantity, the semi-perimeter, so like the average, well, half of the sum of all of the sides, half of the perimeter, and then these products of the side lengths subtracted off from the semi-perimeter, and then you take a square root. So yeah, it's a nice exercise in elementary geometry to prove this formula, but certainly I never learned it at school, so it's quite a beautiful formula. And there are actually many sort of Diophantine problems associated with this formula. So for Heron triangle, so one thing is, if you sort of look at this formula and you think of S as being like a variable and then delta as another variable, you could think of this as being a quartic plane curve. So this would be a genus 1 curve, typically for all these four distinct roots on the right hand side. So there are many problems about sort of Heron triangles, which are triangles which have integer sides and integer area, or if you allow scaling freedom, you can just allow everything to be rational. So say that the sides A, B, and C are all rational, and also the area is rational, and so that's already a slightly non-trivial problem to see when can you get a rational area from this formula. And in fact, the construction, I'm not sure if Heron figured that out, but Brahmagupta, who was an Indian mathematician, I think about 6th century, Brahmagupta came up with a way of parameterizing Heron triangles, so triangles with rational sides and area. So you have 3 rational parameters, P, Q, R, and that gives you ways to parameterize the sides. And Brahmagupta's formula, actually, if you think about it a little bit, if you just take a Pythagorean triangle, so just a normal Pythagorean triple, then that's automatically a Heron triangle, because the area will be rational if the sides are rational. And then you can then stick together 2 Pythagorean triangles with the same height, and that's basically where Brahmagupta's, if you can kind of derive Brahmagupta's formula. But if you have 2 triangles with the same height, you can either put them sort of back to back like that, or you can also overlap them like that. So that would be another way to get a Heron triangle from 2 right triangles. So there's sort of 2 ways you can do it. So then once you've got a Heron triangle, you can ask for more. So you can say, well, what about having other lengths in the triangle being also integer or rational? So as I said, we want to be free and allowed to scale everything, so think of everything as being rational numbers. So what about the medians of the triangle? So I've drawn a picture of a triangle with A, B, C the sides, and then K is the median here of the side A. And so then you can ask, can you find a Heron triangle with a rational median? And then you can go further. So there's what's called a perfect triangle. So a perfect triangle would be a Heron triangle which has all of the medians rational as well. So this is a very rare beast. I would say probably a unicorn, because it's strongly expected or suspected that there are no unicorns, there are no perfect triangles with 3 rational medians. And so you can find, I mean, this problem is described in, there's a nice book of Richard Guy, Unsolved Problems in Number Theory, and this is one of the problems he puts there, and he says there are many incorrect proofs that there are no unicorns, that there are no perfect triangles. And so, okay, so you can also write this kind of nice quadratic formula for the median length. So you've got sort of k is the median of A, L is the median of side B, and M is the median of side C, and you have these formulae. So again, you have to take a square root. So generally, even if you have rational sides and even a rational area, so a Heron triangle, then even finding one rational median is non-trivial. Let's try and sort of maybe ask for a bit less. So what about Heron triangle with 2 rational medians? So Schubert actually gave an answer to this question and said, no, you can't even have 2 rational medians. But if you saw the title of my talk, it wouldn't be a very interesting talk if Schubert was correct. So Schubert has this nice little pamphlet, Die Ganzteiligkeit in der algebraischen Geometrie, and it's a funny little booklet which I bought. I found a copy of it in the pandemic. It's he gave I didn't realize Schubert never had an academic position. He was a school teacher. He never got a sort of university position, but this book is about the title, you could say, it means integrality in algebraic geometry. So looking for integer solutions of of integer points on algebraic varieties of sort of arithmetic geometry, maybe Graf-Einstein geometry. So that's what it's about. And he starts off talking about Pythagorean triples, and then he talks about Heron triangles and gives a nice way to construct them. And this book pamphlet was from a meeting for philologists and school teachers, and he gave this talk about this sort of arithmetic geometry topic. But he said, this is a very nice topic. As a school teacher, you should teach your children your school kids how to build Pythagorean triples and how to build Heron triangles, and he was very enthusiastic about it. But one of the things he did there is he gave what he claimed was a sort of complete parameterization of Heron triangles with 1 rational median, but actually his formula wasn't complete. It didn't include all the cases. And so what he did was then, on the basis of that formula, he set out to show that then you couldn't have a second rational median. So then that would be impossible. So then a perfect triangle is totally out of the question. So this was 1905. So then in the sort of 80s, a guy called Ralph Buchholz was in New South Wales in Australia, in Newcastle University, did a PhD about sort of, let's say, Diophantine properties of triangles. So he was looking at all kinds of properties of triangles. I don't know if my little writing's here, but that's the PhD thesis from 1989. And he gave an emphatic yes to the answer that you can have Heron triangles with 2 rational medians. And this is the simplest example. So 26, 51, 73 are the sides. The area is 420 from Heron's formula. And then the medians are 35/2 and 97/2. So that's a sort of nice scaling, the simplest scaling where all these sides are integers, the area is integer, and the side lengths are co-prime as well. So there's no sort of common factors of any of the lengths. Okay, so that's a sort of minimal example. And how did he find it? Well, he looked at all kinds of parameterizations of triangles, Heron triangles, and rational medians, and then he ended up doing some big computer search, and he found like a few examples, just a handful of examples, but actually somebody else in the US almost exactly the same time, was also thinking about the problem and also doing a computer search. And then they got together and they sort of pooled their resources, and they wrote a very nice article in then a little bit later in American Mathematical Monthly. And it was a mixture of sort of empirical results that they'd found by computer search, and some, you could say, some theorems, and then some conjectures which were very beautiful but without any apparent proof. What I'm going to explain in the talk is how I managed to prove their formulae for Heron triangles with two rational medians. Because what they found, I've kind of skipped it. I've forgotten what's on the next slide, so I'll have to I don't want to give you too much information for the introduction. Okay, well, this is a good thing to look at. So this is like experimental data, you could say. So these are the smallest examples of Heron triangles with two rational medians. So I've got the side lengths ABC, the median lengths KL, and then the area. So I think probably, the article they wrote together was sort of in the late 90s. This is sort of thinking of it as really a Diophantine problem. So you write down the equation for the Heron formula in terms of A, B, C, and delta. Then you write down the two equations for the two medians. And then you can think of that naturally as a surface in a weighted projective space, if you want to think of it like that. Because basically, the side lengths and the medians have dimensions of length, and the area has double the weight, if you like. So these are sort of weighted homogeneous equations in these parameters, and then you want to find rational points on this surface. Okay, so that's sort of, if you want to think of it geometrically, that's a nice way to think of it. That's not exactly the way that they searched numerically. So trying to solve these Diophantine equations numerically is very labor intensive, very laborious. What they did, in fact, was use, in his thesis, Buchholz found a parameterization of rational triangles, so rational sides, with two rational medians. So forget about the area, just fix two of the medians to be rational. And then you can find a parameterization of the side lengths if you want the medians to be, two medians to be rational. Then you have two rational parameters, theta and phi, in this formula, and there's another rational parameter tau, which is just a scale. So again, because you always have scaling freedom, so in a way you can forget about tau, you can fix it to be 1. And then what you can do if you want to do a computer search is you can order rational pairs by height. There's also some bounds on these parameters to really get a triangle, because the triangle inequality has to hold. So, but to get a real triangle, not a sort of collapsed triangle or something, and then check. So you can search by height. You can order the pairs of rationals by increasing height, just naive height, and then check, is the area rational. So that's like a big computer search problem, but it's not as bad as trying to do a search over in these equations. So then I'll sort of just comment on the table now, and I guess tell me when you want me to stop, if you think I should stop now. But I'll say a couple more words, and then if anybody wants to leave, you're most welcome to leave. Just to comment on the table. So what they found was, I think originally up to 1997, they found up to this row, and I think they also found the last row. And then I should comment about the labeling, the first column here. So there's an integer n, and it looks a bit strange. So I've got 1, 2, 3, 4, 5, and then I've got some asterisks. And what this is, well, in fact, what they found, and they did eventually come up with a proof for this, but actually a bit later than this paper, they found a conjecture for an infinite sequence of Heron triangles with two rational medians. And it turned out to be related to rational points on a particular elliptic curve, and later they were able to prove that any rational point on this elliptic curve would give you a Heron triangle with two rational medians. And they also found a formula to sort of parameterize the triangles, the lengths and so on for the triangles, and it basically was involved some special integer sequences called SOMOS 5 sequences. So what I'll explain in the rest of the talk is how you parameterize, well, how you can actually prove that there's this infinite sequence of solutions which are parameterized by these integer sequences which are related to sequences of points on an elliptic curve. And then actually what that leads to is a new formula for the lengths of the sides of in this infinite sequence of triangles. But what's still mysterious is these rows where there are asterisks. So they found originally star, double star and triple star, which are examples that they found from computer search which aren't related to this infinite family that comes from an elliptic curve. And then a little bit later they even found an even larger one down here with 4 asterisks. And so at the moment that's still just completely open. So I mean, yeah, Diophantine equations, I'm not an expert in Diophantine equations, but Diophantine equations are very hard and hard to solve, and it's very hard to make general statements about, you know, what all of the solutions could look like. So whether there could be just one infinite family and just a few sporadic, you know, curiosity examples that don't fit into any pattern, or whether there are more infinite families to be found. So if anyone has any ideas, I'd be very glad to hear them. So anyway, what I'll talk about is, you know, more explicit formulae for these solutions of these equations, and then how you prove them, which basically involves actually essentially doing an analytic embedding of this elliptic curve in the surface. So it involves sort of essentially complex analytic formulae working with elliptic functions. And then also to fully prove the formula, you also need to look at real points on an elliptic curve. So look at actually a dynamical system and look at real orbits of a dynamical system. And then finally, if you want to address coprimality of the sides, you also have to do a bit of arithmetic in finite fields. So you have to look at actually look at points on the curve in finite fields to kind of finish off everything. So it's a mixture of different types of techniques, different types of analysis of geometry. So okay, so please feel free to stop there. Let's have a break there.
Are there any post-trailer questions?
I just lost there was one question, first question with the all integers.
You mean on the previous slide? You want me to go back? Yeah.
So that was
it this one?
No was the answer.
So the question is, can you have Heron triangles with two rational
No, the
medians?
first question.
Oh, the first question is, can you have? Well, nobody knows the answer. So is there a perfect triangle? So can you find a triangle with a Heron triangle with 3 rational medians? So it's still an unsolved problem, but it's a very hard problem. So I mean, one of my motivations for working on this problem was that I hoped that you might be able to rule out that you could have a third median. Okay, so I've mentioned that there's an infinite sequence, so people have used some techniques in Diophantine geometry to prove that none of that infinite family can have a third rational median. I mean, you're always taking a square root, but if you wanted to prove that for all of that you never get you never get a rational number, you have to then do some more work. So it in fact involves some arithmetic of genus 2 curves, and to actually prove that none of those things give you, so there's something called Chaboty, effective Chaboty, that allows you to talk about, you know, integer points on genus 2 curves, which is sort of like Fulton's theorem and so on, but making it effective. So yeah, so the point is that it's still an open problem, and I was hoping that if I could say what are actually the conditions to have 2 rational medians, if we can pin that down, then we could, if we can describe all of that, then we might be able to attack the really hard problem. But so far, it doesn't help. So I mean, I tried to solve it in the most general way possible, but in the end, it just funneled me down to this one infinite family. If you like, I made some assumptions about the shape of the solution, and that it would maybe be described by some, family of elliptic curves, some elliptic functions, and so on. But at the end, it forced me to pick this one sequence of points, or two sequences of points on just one particular elliptic curve. So, yeah, but good question, yeah.
So does that rule out, for example, that the asterisk solutions come from elliptic curves?
No, it doesn't, because again, I was hoping that by taking a very general enough formula, I would be able to find, other families, even with two medians, that would give me other elliptic curves. But again, it pushed me back to the same curve. So but I mean, yeah. At the end, I can show you some data about those examples, because they still. I mean, the main data you're looking at is actually prime factors. So you have to look at prime factorization and then see some kind of pattern in prime factorization, and that's what Buchholz and Rathbun did to get their formulae. So yeah, do you want to ask another question?
It's very interesting.
Yeah.
I have a second. So there was only 2 for the denominator. Why?
Oh, you mean here?
The next slide. The next.
Sorry. Oh, yeah. Okay. I mean, I don't know. That just seems to be a coincidence. So sometimes both of them have a 2, and some of them are sometimes only 1. There is some pattern of mod 2 kind of thing, of modulo the prime. I mean, the divisibility modulo the prime 2. I mean, in fact, well, but I mean, yeah, that seems to just be. I mean, maybe there's an elementary reason. I'm trying to think. But once you assume that A, B, and C have no common factor, and then that K and L have to be rational, you can probably look at. So then basically it means that. I think it means, one of A, B, and C. It's a bit like Pythagorean triples. One of them has to be even, and then the other two have to be odd, and then probably that allows you to assume something about the denominators that could possibly be in K and L once you've made them. So I mean, of course you could just scale everything by 2 and remove them, but I sort of chose the A, B, and C to be in kind of minimal integer form. Yeah. So.
But can it be 3?
No, I mean it's not. I mean I know it's not for this infinite family. I know it's not, but but actually I haven't thought about the stars like whether there's a way you could, if you assume that they're coprime, coprime triple ABC.
But for infinite family, it's integer or half integer.
Yeah, it is always. Yeah. Well, actually, I mean I've got a formula. I've really got a formula for them, like an explicit. Sort of formula, which I can flush up the formula if you want, but it takes a little bit of time to explain. So
all those examples in the had numbers look like they were very, very, very skinny, long, skinny triangles.
Yeah, they are sort of long, skinny triangles. Yeah, that's true. So the point is that there are these 2 integer sequences which are called Somos 5 sequences, and I'll try and explain about these, how they're related to elliptic curves and so on. And these 2 sequences are sort of related to the same elliptic curve, but sort of one of them is shifted by 2 torsion, essentially. And then the point is that once you have these infinite integer sequences, you can prove they have some minus signs, which is also a painful thing to deal with. But once you have that, you can write A, B, and C in terms of combinations of products of these homogeneous combinations of these integer sequences, and then K and L. There's always a factor of half. So that's actually how I know there can't be a 3 Anton, at least for this infinite family. I mean, somehow you almost want to get rid of. You want to take 2K rather than and 2L is the variable swing weight. They're just, they are what they are. So, and the area is also given, it's like a product. So yeah, these are the formulae that I found which are new, but they were based on, I looked at some conjectured formulae that Buchholz and Rathbun had, and then I was able to find it. Yeah.
Just really quickly, I'm not familiar with the notation of a weighted projective plane. Like,
Oh, yeah.
What does that mean?
Oh, sorry. You mean the weighted projective plane? Well, okay. So if you think of ordinary PN, then you would think of that as just like, let's say, homogeneous coordinates. So like n plus 1 tuples. So where, if you like, this n plus 1 vector can't be the 0 vector. So that's just a, and then you can think, but then you can also think of it as a quotient of Cn quotiented by let's say by a scaling action where you basically send xj to lambda xj, and so you identify all those tuples. And so the point is that if you want to work with like this weighted space, then it's like you have sort of, it would be like C6 quotiented by another relation, but then the point is that you take delta goes to lambda squared delta, and then A, B, C, KL goes to lambda A. That's just right. Yeah. So that's all. It's just the equivalence relation is weighted for the different variables. That's all. Yeah.
All right, let's actually shake off for a second and start the real talk. Looks like
Yeah.
the
You're ready for
whet the appetite. But yeah.
Okay.